This is Mr. McCord's AP Chemistry class. We're continuing into equilibrium to tack on kind of a new thing we can do with it. We're going to look at expressing solubility products as a solubility product constant. This is basically just going to be another application of big letter K, our equilibrium constant. And I'm also going to touch on how this can be used in other ways we'll probably see kind of ahead in Unit 8, Unit 9, and so on. So, up to this point, we've used the equilibrium constant or a reaction quotient to relate the products on top to the reactants on bottom with the coefficients of the reaction out as exponents for each reactant or product that shows up in the expression. Okay? The Q, the reaction quotient, is the same as K if the reaction has reached equilibrium, where the rate of the reaction forward is equal to the rate of the reaction reverse, which could mean you've got more reactants, could have more products, or one of them is predominating over the other. It doesn't matter, but we can tell based on what our value of K or Q is. Specifically, our Q tells us which way the reaction needs to shift towards, either the forward direction or to the right, okay, or the reverse direction or to the left, in order to reach that equilibrium point. Okay, and again, may not be at equal concentrations or pressures, and probably isn't. Okay, it's probably going to be very much to one side or the other. Okay, and there are a lot of reactions that are reversible in chemistry. There are only a few here and there that are chemical processes that just go one way. So things like that are very, very thermodynamically favorable. Things like combustion reactions or a lot of single replacement reactions go one way, and that's it. If we get into electrochemistry, there are quite a few reactions there that have a strong enough difference in energy from start to finish that it's really not very feasible to go back the other way in the reverse direction. Okay? But a lot of times when we're dealing with aqueous chemistry, stuff being dissolved in water or otherwise in solution, we get all kinds of stuff that can be reversible with gases as well. Okay, so our K is kind of a multi-tool. Okay, our expression of products to reactants can tell us a lot about any reversible reaction, but sometimes we will denote it with a little c, specifically for measures of concentration, like with aqueous solutions or gases, or a little p for pressure for a gas-only reaction. The QC can be used for heterogeneous reactions, so things that might have a couple different phases of matter, like gases and aqueous components. Okay, but sometimes we will also have for specific types of chemical processes. So these first two here are related to acids and bases. When you take a strong acid or a strong base and you dissolve it in water, okay, they completely dissociate into ions. There is no leftover molecular version of the acid or the base together. Okay, it always breaks up totally into its ions. Okay, so anytime you deal with a strong electrolyte like that, we're not going to have a reversible reaction. It proceeds so much in the forward direction, there really isn't a reverse direction. Okay? At least not, at the scale that we are concerned with. It's negligible at best. Okay? So, in this case, we are looking at a weak acid or a weak base and how they partially dissociate in water. So, for our acid, we donate an H+ to our water, which picks it up and becomes a hydronium ion. That's just a fancier way of saying H+ in solution. It's water that has been protonated. It's picked up that H+ proton from the acid. So we're now dealing with an acidic solution. The leftover anion here, the A-, is our conjugate base. Okay? And it can reversibly kind of go back in the other direction where our conjugate base might pick up an H+ and remake the molecular acid. Okay, so this would be basic because it's picking up an H+. Okay, we also see our weak base down here that takes an H from water. All right, so it accepts a proton from water. We're left behind with OH- that makes our solution basic, and we have a conjugate acid over here that could re-release that H+, in terms of how an acid would work, and so on and so forth. Now, we're not really super worried about acids and bases here, but this is just the kind of application we can do with this. And when we write out an equilibrium constant expression for a weak acid or a weak base like this, typically we'll give it a specific little letter down here, kind of to denote that it's about a weak acid or a weak base. So for weak acids, we use a little A, so Ka is what we call it. Okay, or for bases, we'd have a little Kb. But they're no different than any other K expression. So sometimes on equation sheets, you'll see something lay out like, this is what a Ka looks like, or a Kb looks like. But you can make that yourself if you got the reaction equation. It's no different than any other reaction at equilibrium. Okay? So those are two examples that you might kind of run into in the future. Acid dissociation constants are also kind of what this is called, or base dissociation constants are a lot of times what these guys are called. Okay? But what we're going to focus on is what happens when we have something that's usually insoluble still kind of break up into ions and still kind of have those ions come back to reform the solid. Okay? Precipitates, will precipitate, and up to this point we've kind of thought about it as a one-way procedure. We have these ions that, break apart their ionic bonds and float around in the water, and water surrounds them, and that's favorable, and we're like, ah, cool, great. And for insoluble stuff, we're like, well, they just stick together. They don't break apart. But a lot of times they do break apart just a little bit. It's a partial dissociation, just like a weak acid or a weak base. It's a weak electrolyte. Now, some of them are so weak that, you really can't tell. It's also pretty much negligible for that ionic compound to break up even a little partially. But theoretically, we can still write out an equilibrium constant expression for a precipitate, where our products, the stuff on the right, are going to be the ions that thing would usually split up into, even if it's not very common, even if it doesn't happen all that much. Okay? And our reactant is going to be the solid precipitate together, that insoluble chemical, that ionic compound that is just not giving it up. Okay? So, with an ionic compound, it may be that it is a strong electrolyte and it can totally break up, but it just doesn't do so in a complete fashion. Every time it does, it will break up totally into ions, but that doesn't mean it's going to totally dissolve in your solution. Okay? So, when we deal with something like this, it's also a reversible process, and therefore we can write an equilibrium constant expression for it. Okay? Now, because we're dealing with stuff that is dissolving, this is all about solubility, how many ions we can fit into a solution. Okay? We also have a situation where whenever we're writing out a precipitate breaking up into its ions, we've always got a solid on the left, we've got aqueous stuff on the right. Okay? If you remember, we don't put solids or pure liquids into an equilibrium constant expression, we leave them out totally. Okay? It's like they're not there. So like our water as a liquid in our acid and base stuff does not show up over here. Okay? Our solid that we're starting with here also does not show up. So we have nothing on the bottom of our KSP expression here. Okay? So the KSP is basically an equilibrium constant for the product of these soluble ions. So we call it the solubility product. Okay? We have these guys up on top, whether it breaks into one ion or two or three, whatever. And then we don't have anything on bottom because we write it with the solid as the reactant on the left, just kind of by tradition. So the forward direction is going to be breaking up into the ions. Okay, so this is what we call the solubility product constant that relates the concentrations of those ions when it is as saturated as possible. That means we have shoved as many ions as we can into the solution. Okay, for some compounds that is very concentrated. For others, it's barely concentrated. Only a little tiny bit will actually break apart into those ions. Okay, so just like, again, any other equilibrium constant, like a broken record, this can tell us kind of the extent to which a compound will dissociate into its ions based on how big or small the K is. We compare that to whether the products on top are kind of predominating or the reactants on bottom are. In this case, our reactants are just going to be 1. And a lot of times you'll see this totally left out. So you'll see that the KSP is only, 1 ion times the concentration of another ion. over nothing. They don't even bother to put the 1 underneath. Okay, so we're going to look at how we can write out solubility product constants, how we express that, and how we solve for either the KSP, okay, or using a value of KSP to figure out how soluble one of these ions or both of them is in solution using some algebra there. Here we have some precipitates that would typically not dissolve well in water, but do to some extent. All right, so again, we write this out with the solid on the reactant side. So the product side is the ions that they would break and dissociate into. Okay, so our KSP value, just like an equilibrium constant of any kind, would tell us the ratio of kind of forward to reverse, what side predominates, either the products or the reactants. Okay, if your K value is bigger than 1, that means your number up on top of your expression is kind of winning out, which means that we are dealing with a more predominating product. Okay, now we also can say if we've got something that is very, very small, right, like less than 1 or very much less than 1, something with like a 10 to the negative attached to it, that's a good sign that we are hanging back towards the reactant, okay? And that's what we see with a lot of solubility product constants, okay? So these are just a couple of examples. We've got calcium carbonate, aka calcite, if you are into geology, or it's also in eggshells, Tums tablets, all kinds of stuff, okay? Calcium carbonate breaks down into Ca2 plus and CO3 2 minus, and the solubility product constant that comes out for this is about 4.5 times 10 to the negative 9th. Again, unitless because it's a K value. And this is at 25 degrees Celsius. Just like any other equilibrium constant, if you change the temperature, you change how well it dissociates, how it dissolves, etc., etc., etc. So this is specifically for 25 degrees Celsius. You can find sample dissociation constants in Appendix D of your book if you're using Brown and LeMay, the Chemistry, the Central Science. And again, these are all at 25 degrees Celsius. So if you are dealing with a practice problem or a homework problem or a lab problem and you're just looking for an easy answer, just be aware you can't just grab it from the book if you're not at 25 degrees Celsius. So you might use it as a reference, but don't use it as an answer. Okay? Silver chloride is a common precipitate that we like to use in chemistry education because typically it looks pretty cool. Okay, breaks up into Ag plus and Cl minus. And our equilibrium constant, our solubility product constant in this case, comes out to be 1.8 times 10 to the negative 10th. Comparing these two, okay, times 10 to the negative 10th means that we're moving another spot to the left. Okay, and this 1.8 is also smaller too. So this is shifted more towards the reactants. The reactants are kind of more favorable in this case, which means it's not as soluble, okay? So we can interpret what's going on in the process as well, just like with any other reversible reaction. So our AgCl is not as soluble. It's not able to dissociate as completely as our calcium carbonate is. And even more so for our calcium fluoride here that breaks up into Ca2 plus and 2 F minus ions. Okay? Now, the way something dissociates determines your concentration of Ca2 plus ions or F minus ions or Cl minus ions, so on, so on, so on, in your solution. So just knowing the solubility of the precipitate kind of compound that you're dealing with or the KSP doesn't kind of answer everything that we need. So we do need to look at what the expression is and what our relationship of our products together is to figure out how concentrated those ions are in solution. Sometimes they will be equal to each other because as your AgCl breaks up, it's going to make one of these and one of these. So however much your Ag plus concentration increases by, your Cl minus concentration will also increase by that. If you're starting from only solid and no ions, then if they're both starting at 0, they should increase by the same amount and end at the same amount. But there are also a couple of hitches. Sometimes, like with this calcium fluoride, you don't have an even ratio. Okay, so one of these will make one of these and two of these. So your concentration is going to change by twice as much for this fluoride ion as it will for this calcium 2+ ion. Okay? And we might also already have some stuff floating around in the solution. So maybe I'm not starting with just AgCl solid. Maybe I've already got some Ag ions floating around in there. Maybe I already have some AgCl ions floating around in there, or both of these. Maybe there are different concentrations, okay? Or maybe it's just one of them. I could throw in a compound that just has one of these ions, and that can still affect the equilibrium because there's already some concentrated amount of ion there, okay? So we can do some math to figure out how these sort out. In this example, we were looking at AgCl, a precipitate, right, that is in a reversible reaction with its ions in solution, and we want to figure out the molar concentration of Ag+ and Cl- ions that are in this solution of AgCl. Not only that, but this is saturated. KSP is kind of defined as being all about that saturation, where this has dissolved as much as it can, okay? So we're not really focused on the Q, the reaction quotient aspect, where it's like how much more of this is going to get us to that saturation point, or have we passed over it and need to go back? We're going to be looking solely at just how does this work at equilibrium, okay? So with any equilibrium problem, we're going to try and set this up to see what our K expression is going to look like, okay? If we have something about the change of things or the KSP value itself, we can start to try and work out what the concentrations within this are. So let's work it out. So our KSP expression should be products over reactants. Our reactant is a solid, so it's not going to show up. So I'm only going to write products. So Ag+, and it's in solution, it's aqueous, so I'm going to put brackets around it. I'm going to make it a concentration, a molarity. And my Cl- ion is in there. Again, if you wanted to, you could put a little imaginary 1 there just to represent, oh, the reactants would be there, but we don't really need to. It's just kind of clutter, so I'm going to get rid of it. Okay, we're given that our AgCl solution starts with no AgCl before we throw this in. So we take this AgCl solid, and we drop it in pure water with nothing else in it, and we dissolve it as much as we can. So we want to see how much of this winds up kind of dissolving and breaking into its ions at this point of equilibrium. Okay? We have the KSP value already, so this silver ion concentration times the Cl- concentration should come out to be this number here. So we're going to need to use that. Okay, so let's set that up. So the product of these Ag+ and Cl- guys is going to be this 1.8 times 10 to the negative 10. Okay. Now, at this point, I'm kind of stuck because I don't know the concentration of either of these ions at equilibrium. So I can't really solve for these if these are two different variables. The nice thing is these are actually the same thing. If we kind of look at this ice chart over here, red marker, our AgCl is a solid, so it will not kind of participate in our equilibrium constant at all. Our solubility product constant, or KSP, is not going to include this, so I'm just going to put dashes there for those. Okay. Now, our Ag+ and Cl- are going to show up, and if we're starting with none of either of these, that means whenever our AgCl breaks up, it's going to make the stoichiometric kind of ratios of these two ions. Okay. AgCl breaks up into one of these and one of these. Okay. So anytime I make some kind of change, I should get the same concentration change here and here. So I'm going to write that as plus a variable. You could use X or a question mark or whatever, but since we're kind of dealing with soluble stuff, what you'll see a lot of times is a little s, or sometimes a big S. I like to use a little s because we kind of use big S for entropy, and I don't want that to get kind of muddled in. So our change is going to be increasing the concentration of our Ag plus and our Cl minus by some amount S, okay? Which will take us to our final concentration, okay? So if I take 0 molar concentration plus S molar concentration, I'm going to wind up with S molar concentration. Okay. Now, does that get me any closer to figuring out the concentrations of these? Maybe not necessarily, but what it does do is it puts me on common ground with these ions, because now they have the same variable. It's like using the x's we've done before in these kind of expressions. So, I'm going to replace the Ag plus and Cl minus concentration with an S. So this is now representing the unitless concentration of the Ag plus ion and the Cl minus ion at equilibrium, okay, when we have a fully saturated solution. So S times S should be equal to 1.8 times 10 to the negative 10th. Well, maybe Ag plus and Cl minus before were kind of seen as two different things, but I can multiply an S and an S. That's just easy algebra. So S times S is going to be S squared. And that's still going to be equal to 1.8 times 10 to the negative 10th. The last thing I would need to do is figure out what this S equals. Okay? And to do that, I need to get rid of this square. So how do I undo a square? I square root it. So I'm going to square root both sides. Okay, both sides are square rooted, so this is going to be just S. S is going to equal whatever 1.8 times 10 to the negative 10th square rooted is going to be. Okay, so I'm going to go grab my calculator, try it for yourself. Okay, and don't forget to put everything in parentheses when you square root it. Make sure it's all included in the square root. Otherwise, you might get an answer that's square rooting the 1.8. but then just multiplying by 10 to the negative 10. That will be a different answer. My S came out to be about 1.34 times 10 to the negative 5th. Okay, we're going back into a molar concentration for this. That's what would be plugged in if we weren't kind of ignoring the units for our KSP. Okay, so what that means is that our Ag plus ions and our Cl minus ions both have this concentration in the saturated solution. All right, now what can throw this off is if we were to already have some Cl minus ions floating around, or maybe some Ag plus ions floating around, because we wouldn't be starting at a concentration of 0 molar anymore. Or maybe we go and mess with the temperature, or we have something else going on to kind of shift this around. Okay, so these problems can get harder. Okay, now something else you might be asked is not the concentration of the ions at equilibrium, but you might be asked for the molar solubility of something. Molar solubility is still measured in the same units as molarity. It's moles per liter, but specifically, it's moles per liter as concentrated as it can get in that solution. So basically, when it's saturated, again, kind of goes along with the KSP. So what we're getting here is essentially lining us up to figure out the molar solubility of the original solid. Okay, it's just a way of saying how much of this can break up into ions and dissolve. Okay, so because our ions are kind of separate entities that are kind of breaking up and sometimes have a different ratio compared to kind of the original thing altogether, the math can change a little bit, but a lot of times your molar solubility is going to be just like right there. It's basically the same thing. Okay, it might just take a little bit of stoichiometry to say, okay, I had this many ions of this break out, like 2 or 3 ions of this from my original one. So how do I backtrack it to that original kind of empirical formula? Here we have an equilibrium between calcium fluoride solid, the precipitate, and the ions it splits up to, 1 Ca2 plus and 2 F minuses every time it dissociates. We kind of are representing it here in this imaginary beaker or some kind of glassware. Okay, so black atoms here are representing our calcium ions. We've got our white atoms representing our F- ions, not the typical colors that these usually go with, but I had to make do with what I have, and I have more of these colors than the others. Okay? And we can write out a KSP for this. So if I have only aqueous products showing up, my equilibrium constant is only going to show those things. That's what makes the KSP kind of a little bit simpler than a usual equilibrium constant. So my solubility product has the concentrations of my two ion products, where the concentration is how soluble they are, how concentrated they are in a saturated solution. And again, we plug in molar values of concentration without the units. Don't forget the squared, because I've got a coefficient of 2 out front here. Okay, so I can look at this just like any other equilibrium. I can say, well, how is this kind of leaning to the left or right? If I look at the representation here, I've got way more calcium fluoride solid down here than I do the ions that are floating around. So I'm going to have a very, very small KSP. Even though my equilibrium constant doesn't have the reactants on bottom to represent there, the concentrations of these are still going to be very, very small. So my KSP is still going to come out to be a number much less than 1, something that indicates that this is kind of favored to the reactants side, because this is kind of what's more represented. We barely have any of this in comparison. Okay, so, I can do that. That's good. But I can also go and mess with this. When we looked at Le Chatelier's principle, we can change temperature, and we can change concentration and pressure and stuff like that to mess with the equilibrium, see how it shifts. So we're going to do something similar to that. We're going to use an application of Le Chatelier's principle specifically for some soluble product in water, even slightly soluble, that we call the common ion effect. So the key thing I'm going to say first is this is no different than anything else we've done before, but it has a new name, so don't let that freak you out. So let's take an example. So we take this calcium fluoride solution, and we add it into a solution of sodium fluoride, which has broken into Na plus ions and F minus ions. Okay, so we already have some concentration of ions floating around in this solution. There is what we call a common ion between these two solutions. We've got our F minus here, and we've got our F minus here. Okay, so we already have some of this stuff in the solution. Now, it can also go the other way. It doesn't really matter whether you put the calcium fluoride solution into the sodium fluoride solution or putting the sodium fluoride into the calcium fluoride. Either way, when they get mixed up, we're going to have two solutions that have one thing in common, and that is, in this case, this fluoride ion. Okay, well, our KSP for our calcium fluoride depends on that fluoride concentration. As long as I'm keeping this at a constant temperature, that KSP number should come out to be the same, I'm going to point at it, same thing. Okay, so if my F minus concentration is going up as I am adding this F minus here, then something has to happen in this equilibrium to offset that. Okay, if this concentration of fluoride is getting higher, then I need to lower this concentration of calcium. Otherwise, my KSP is going to come out different. So my equilibrium is going to be shifting here. Well, which direction does the reaction need to shift in order to get my KSP to level back out to equilibrium? Well, if I want to use up the Ca2 plus ions and put it back into a solid, I've got to drive this reaction to the left so that it favors the reactants even more than it already does. Okay? You could say that this changes up the reactant quotient value such that our Q is now bigger than our K, but typically with KSP, it's kind of like, well, we've seen in that, we've done all the stuff with reactant quotients, and we're just going to jump straight to how does the reaction shift, okay? So, what does that mean for this reaction? Okay. Well, if I go and add in this sodium fluoride, okay, and I now have more fluoride ions in there, okay, I have to kind of rebalance this using the stuff that was already in there. So if I'm going to push this reaction back to the left side, I'm going to have a rate of reaction faster for the reverse reaction for this calcium fluoride. You might notice that my sodium fluoride just goes to the right. It's not reversible, so those ions are staying there. But I can't really distinguish one F- ion from another. So once I already have those F- ions in there, they're going to get pushed back into the CaF2 somehow. So some of this is going to have to precipitate, right, back to the solid. Okay, well, what does that mean for this snapshot here? If I'm looking at how soluble this CaF2 is, solubility of CaF2, well, typically we look at molar solubility, how many moles of CaF2 we can dissolve, how much we can therefore break into those ions. I now have less of those ions and more of the solid. So what does that mean? It's now less soluble. My solubility of my CaF2 has gone down. So I've decreased the solubility of the calcium fluoride. I didn't have to change anything about the calcium fluoride specifically. I didn't need to change the temperature. All I did was introduce more of this common ion that was in the equilibrium that was going on. To counteract that, the equilibrium reaction shifts back more in the reverse direction to use it up, and we wind up with more of the solid here. Okay, we end up precipitating more out. Okay, so hopefully it's clear that this is just Le Chatelier's principle. It's really no different. The only difference, technical-wise, is that we're now calling it the common ion effect because we're focusing on the concentration of an ion that is in common with these two solutions, okay? But what happens is really no different than any other reaction or system in equilibrium, that is aqueous with ions floating around, okay? So, no change in temperature necessary when we change the solubility of this CaF2. And you can do examples with this with, an ice chart where you are starting with some concentration of F- or some other ion. Maybe I throw in some calcium chloride, okay? The Cl- ions are not going to do anything, but the Ca2+ ions will. It would be the same idea. If I increased this concentration, I would need to decrease the concentration of F- to get everything back level, ratio-wise. So my reaction is going to arrive to the left. Let's look at an example of how this might play out with some math. So we have our KSP up here for our calcium fluoride dissociating into its ions. It should be equal to 3.9 times 10 to the negative 11th at 25 degrees Celsius. And we're assuming that we're keeping that at the same temperature throughout this process. So, for kind of the sake of simplicity, we're going to say that we're adding in this calcium fluoride solution into a solution of sodium fluoride that's already been made up. So if our concentration of our solution of NaF is 0.026 molar, well, the NaF is going to break up into an Na plus and an F minus. So a mole of NaF makes a mole of F minus. So whatever our concentration of NaF is together should be our concentration of F minus separate. So what we're starting with is some concentration of F- ions already. Okay? We go and combine these solutions, and they have to reach equilibrium to get back to this value of the KSP, which we should expect to have been thrown off by this F- concentration that's gone up. Okay? So, to shift the reaction back to the left to favor the reactants, we've got to go through some change, and we should have some new concentrations at equilibrium. But other than the KSP value up here that we have, and these starting concentrations, we don't really have much else to go on. So let's just plug in what we have and see where it takes us. Okay? So, we know our KSP. Should be 3.9 times 10 to the negative 11. And we need to know the concentrations at equilibrium. We're going to end up solving for them. So we need to have something in here that we can kind of substitute for and calculate. Okay? So I need to know how much this is going to change by. Okay. Well, based on my calcium fluoride dissociation reaction I've got up here, one of these should break into one of these and two of these. So I can show that relationship in my change row here, because every time my CaF2 breaks up, I should make one more of these and two more of these. So my relationship should be that I am changing the concentration of my Ca2 plus by X every time I change my concentration of F minus by 2X. Okay, not so bad so far. Okay. Now, I can make an expression of how concentrated these will be at equilibrium based on the changes in X here. So 0 plus X is just going to be X. Okay, that's not too bad. Okay, and then, well, 0.026 plus 2X is just going to be 0.026 plus 2X. So I guess I can't really smush those together. So let's try plugging those in. Okay, my Ca2 plus concentration was right here, so I'm going to put my X in there. Okay, and then I've got this 0.026 plus 2X right here. Okay, so I'm going to need to kind of work this out a little bit. So I've got to square both of these, okay, to kind of get everything worked out. So I'm going to have 0.026 squared, and then 2x is also going to be squared. And then I'm going to have to multiply it to this x here. So I'm going to condense this part first. I'm going to plug in 0.026 squared into my calculator. My 2x squared should just be 4x squared. Okay, so we've simplified this down a little bit. We now have our x times that 0.026 squared was 6.76 times 10 to the negative fourth, aka 0.000676, plus our 2x that was squared. That gave us 4x squared. Now here's where our math is going to go a little bit rogue, because if you distribute this out and do the x times this and times this, you're going to get something with a cube in it, so it's going to be like 4x cubed, and then there's just, there's no way out of it. I mean, if you're really good with the math, you could probably, you know, chop it down, but the truth of the matter is, if we look at what this x is going to be, what the change is that's going on here, it is very, very, very small, okay? Even compared to something like 0.026, it's still going to be a pretty dang small number. So when I take a small number plus 4 times a very, very small number squared, that's going to be even smaller. Taking a small number times a small number is very, very, very small, okay? Timesing it by 4 is not going to be able to save it. taking this 6.76 times 10 to the negative fourth plus something so invariably tiny is like it's not even there. We're not even going to have enough significant figures to go out far enough to recognize the difference. So maybe this goes from 6.76 times 10 to the negative fourth to 6.7600000007 or something like that. There's no way it's going to show up in our answer. So to make the math way easier, okay, and also to kind of be real with it, this plus 4x is going to not really do much for us. So we can kind of just get rid of it. So you'll see this sometimes written as like a small x approximation or something like that. But essentially all it's saying is when we are adding or subtracting a very, 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 very small number, like a change in concentration in equilibrium with KSP, it doesn't really affect our calculation that much. So little, in fact, that we can just get rid of it. We just disregard it. Okay? And this is something that will make math teachers and stuff be like, oh my God, you can't just get rid of it. You got to put it back. But okay, we're chemists, so we're just gonna we're gonna roll with it. So we do still need this x over here, and I gotta find the right marker. This is something that used to drive me nuts. Because when people told me this, and they'd say, okay, well, you can get rid of this, 4x squared or something, but you can't get rid of that x, I'd be like, well, if it was so small it didn't matter there, why does it matter here? And it all comes down to the math operation you do to it. Okay? When you take a small number times a small number, that makes it much smaller. There's a big difference there. Taking a small number and adding it to someone else, not so much. Okay, so the fact that this is x times something else matters. Very important. This plus an x or a 2x or a 2x squared or a 4x squared or a 4x cubed or whatever is not really going to do anything. So if you ever wind up with a plus something x in an equation like this, it doesn't have to be 4x squared. It could be some other version of that exponent or something like that. Or it could be just an x without an exponent. We can just kind of get rid of it. So all we're left with is this concentration of x times this concentration of this. There should be some small amount of Ca2 plus that we are going to have at equilibrium, okay? But this isn't going to change that much that our math is going to be affected inside here. So we're just going to solve for x this way, which is so much easier because all we have to do is divide both sides by this 6.76 times 10 to the negative fourth. Okay, so our x, our concentration of Ca2 plus, and what we're going to use to solve this out here is going to be 3.9 times 10 to the negative 11th divided by this guy right here. So let's plug it in. I'm going to put big parentheses around it. 3.9 times 10 to the negative 11th divided by parentheses 6.76 times 10 to the negative fourth, close parentheses. I get, I gotta count the spots. 1, 2, 3, 4, 5, 6, 7, 8. Looks like about 5.8 to times 10 to the negative 8, I think. Let me recount that. 1, 2, 3, 4, 5, 6, 7, 8. Yes. Okay. I'm kind of running out of room, so let me rearrange this a little bit. All right, and all I have to do is finish solving this out. Okay? Well, if my x turned out to be 5.8 times 10 to the negative 8, that's all I have to write there. Because the x I solved for is going to be the equilibrium concentration of this. 0 plus that x is just going to be x, which in this case is 5.8 times 10 to the negative 8. And we're measuring concentration in molar. And then I can take 0.026 plus 2 times that x. And let's see how much different it's going to be than this starting 0.026. Okay, so 2 times our 5.8 times 10 to the negative 8th. All right, plus 0.026. Okay, so just to kind of go to show how much of a difference it makes, this comes out to be 0.026000116. So unless I have 1, 2, 3, 4, 5, about 6 significant figures, which is wild and not likely, I'm not even going to see what this comes out to be. Plus 2x is going to be plus something so small we're not even going to notice it get any bigger or smaller, depending on how this goes. So based on my significant figures, I can basically just wipe out this plus 2x also. So this is going to be my concentration here. Okay. Now in reality, is that going to be a little bit different? Yes. Okay, but not so much in this case. Now, the original goal of this was to see how our solubility of our calcium fluoride changed by this. We should expect it to be lower. Well, we now have a concentration of our Ca2 plus at equilibrium, okay, and it matches up with the ratio of our CaF2. So if one of these is kind of the same as having one of these, then the solubility of this is essentially the solubility of our CaF2. It's kind of the empirically lowest ratio of how this goes. So, essentially what this is saying is we can dissolve 5.8 times 10 to the negative 8th molar concentration of CaF2 in solution. All right? So, kind of the simplest kind of common factor there. Now, is that really smaller than what we had before? We can find out. So let's take a little bit of a tangent here. So we've got our original KSP written out here with our 3.9 times 10 to the negative 11th. So if we were to start at 0 molar of both of these and just let it ride, we would see that we would get 1 Ca2 plus for every 2 F minuses. So we can swap those out for 1x and 2x. Great. Now I have them in kind of a common variable. I can crunch them together. Don't forget that this squared is going to distribute to both the 2 and the x. So that's going to be x times 4x squared still equal to 3.9 times 10 to the negative 11th. Okay. X times 4x squared is going to be 4x cubed. I'm getting rid of my brackets here because I don't really need them at this point. Drop this down. Okay. So if I divide both sides by 4, and cube root both sides, I should get my answer. So 3.9 times 10 to the negative 11th divided by 4, and then all of that cube rooted, I should just be left with x over here. Okay. Now, because our x stands for our calcium 2 plus concentration, this should work pretty fast once we've got this math sorted out. So let's punch this in. .9 times 10 to the negative 11th divided by 4. All right, and then taking the cube root of that, I get my x is equal to 0.000214. Or I could write it out as 2.14 times 10 to the negative fourth. And this is a molar concentration. Okay. Now, remember, our goal is to figure out the solubility of CaF2, and our ratio of Ca2 plus is the same as what it is to CaF2. So we can treat this as the solubility of CaF2. Now, again, a lot of times we'll use a little s or a big S for the solubility of something. So if you want to kind of work up to it, you can also just replace all your x's with s's. That way you don't forget that you got to figure out the solubility. Okay, so my solubility under normal circumstances with no solution of sodium fluoride in there is 2.14 times 10 to the negative fourth. That's still a small concentration for our calcium 2+ ions and for everything else kind of in that solution, but it's bigger, remarkably bigger, than this concentration here. So, yes, our solubility, our maximum concentration of these guys at equilibrium has gone down. Our original solubility is bigger than this concentration. So we have decreased the solubility of our calcium fluoride by throwing in a common ion, in this case, fluoride. Now, you can also do this with our calcium ion. You'll just end up kind of smudging away a different plus X somewhere, in there. You'll just kind of have like a, plus something, mark it out in a different spot. But the process works the same.